So welcome back from the break. We're in the middle of proving the complex spectral theorem, and we already have the equivalence of B and C, and in the last part we proved that A implies C. We use Schur's theorem to get that direction, and now we just need to show that if C is true, that the operator T is normal. So we want to show that if you had some sort of orthonormal basis, such that this matrix is a diagonal matrix, the operator is normal. And so let's walk through the proof of that. Now, if T has the associated matrix diagonal with respect to the orthonormal basis, then the matrix of the adjoint is simply the conjugate transpose of the matrix of the original matrix MT. Okay, and not only that, we also have that because this is a diagonal matrix, when you take the conjugate transpose, you get a diagonal matrix. So we get this is a diagonal matrix. Okay, but now we're looking at kind of at the matrix level. The matrix of T composed with the adjoint is the same thing as the matrix of the adjoint times the matrix of the operator. Now these are diagonal matrices, and so diagonal matrices commute. You may remember that from Math 1B03, so it doesn't matter which order we put them in. So this is the matrix of the operator times the matrix of the adjoint. And then we have here, we can kind of recombine it. This is the matrix of the operator, the adjoint of T composed with T. So because T composed with the adjoint and the adjoint composed with T, their matrices are the same. That can only happen if the operators are the same. So that tells me that the order in which you compose these operations doesn't matter, but this means that the operator is normal. So T is a normal operator. Okay, so that proves the complex spectral theorem. So I just kind of want to give you an example of this. Okay, so let's kind of look at a particular example. So I have the matrix A, and I'm going to look at AB minus BA. And we want to think of these entries as R, but we actually want to think of this matrix as belonging to the set of complex numbers. Okay, so even though the actual entries are real numbers, we're thinking of them as complex numbers. Okay, special complex numbers. And in this case, the adjoint of this matrix is A, the conjugate transpose of this matrix is A minus B, BA. Okay, and we have here that when we take these two matrices and we multiply them together, so we get A negative B, BA times, make sure I get this in the right order, A, B minus B, A. When I multiply them together, I get A squared plus B squared, 0, 0, A squared plus B squared, right here, and that's the exact same thing as if I were to multiply them in the other order. So what's really happening here is that this matrix A corresponds to a normal operator T in the side of the set of complex numbers, or on this vector space CT. Okay, so let me be a little bit more precise. Kind of what I'm doing here is I'm actually working kind of backwards. I'm looking at an operator and I'm trying to, I'm cooking up a matrix with the right properties, and then I'm going to define an operator doing that. So my operator is going to be, takes the pair x1 and x2, and it maps it to ax1 plus bx2 minus bx1 plus ax2. And notice that that's the same thing as taking the original matrix A, B minus B, A, multiplying it by the vector x1, x2, you're getting a vector, and then you're taking the transpose of that. Okay, because normally this would be a 2x1 vector, but we want to write it in this form. Okay, so this is actually the matrix associated to T with respect to the standard basis. Okay, now this operator is normal. Okay, this operator is normal, and that's what we're demonstrating right here that the operator associated to it is normal because the conjugate transpose times A is the same thing in the reverse order. So the complex spectral theorem says that there actually has to be an orthonormal basis of eigenvectors of not T, that actually, let me fix that, that should be of, oh no, that was right. I don't know what I was doing there. V can have a basis of eigenvectors that are orthonormal, and with respect to that basis, we can get a diagonal matrix. Okay, so let's just try to find that matrix for you. Okay, and you could use Math 1B03 techniques here to find out what the eigenvalues are. The eigenvalues here are A plus BI and A minus BI. And the eigenvectors here are, make sure I left myself enough room, 1 over the square root of 2 and I over the square root of 2. And this one right here are 1 over root 2 and negative I over root 2. Okay, and you can check that both have norm 1. Okay, so they both have norm 1. Okay, so they both have norm 1. And the other thing that you can notice, and you could probably do this in your head, is that when you do the standard Euclidean inner product on these two vectors here, you get the zero, sorry, yeah, so these, let me rephrase that again, that these two vectors are orthogonal if you're using the standard Euclidean inner product on C2. Okay, so kind of summarizing up above here is that these two vectors is an orthonormal basis C2. You should convince yourself, okay, of that fact that they actually are orthonormal. And with respect to this basis, the matrix associated to it is A plus BI, and 0, 0, and A minus BI. And there is the diagonal matrix guaranteed that we knew that we could find according to the complex spectral theorem. Okay, so there are maybe some details you might want to convince yourself, but this gives you kind of an example of the complex spectral theorem. Again, let me just put it up, that if you have a normal operator, you can find a basis to make the matrix diagonal. Okay, so when we come back after the break, we will talk about the real version of this theorem.